This morning we're going to be doing the topic of the energy equation. In the previous lecture, we introduced the concepts of pressure and total head. Okay, so if you remember, the total head was made up of the static pressure, the dynamic pressure, and the hydrostatic pressure. Okay, so these were the three components of the total pressure. And if you remember, we actually looked quite carefully at the static pressure and using the static pressure. So this is the pressure that the fluid has by existing, okay, without any motion. So this is like the movement of all the gases or the molecules in the liquid creating a pressure. On the boundary, we had stagnation points. So this is where a streamline comes to a stop, a frictionless stop on the surface of the boundary. The velocity at the stagnation point is 0. Okay, and so that's why it's called a stagnation point. And then we looked at how the Bernoulli equation is used in various sort of flow measurement devices, including the piezometer, the pitot tube, the Venturi flume, and probably the most difficult to understand was the pitot-static tube. And I left you with one final question. So I said the wind tunnel below is powered by a fan, okay, at the end of the channel. So here is my fan, okay, just here. And I want you to consider what happens to a streamline as it goes all the way through. Okay, so what happens when the streamline reaches the fan, and what happens to the Bernoulli equation? So let's just consider the streamlines in the wind tunnel as they reach the fan at the end of the channel. Okay, they've gone all the way through, as you can see there in the image. Okay, they've gone all the way through from the beginning all the way through to the end, and they're about to hit here. But the fan is rotating, okay, and it's rotating quite fast. So that rotation gives the fluid a rotation, and you actually have something called swirl at the end there. So what happens? Well, the central streamline will hit on the stagnation point, but the others will not, and it will start to go round. But the flow becomes much more complicated here because of that rotation. And all of a sudden, you have friction effects, you have viscosity and things like this, which start to become significant. And at that point, you can no longer really apply the Bernoulli equation because it's no longer steady, okay? It's no longer frictionless. So the fan is rotating, okay? And when the fan is rotating, the flow there is no longer steady. The flow is steady, in effect, at the entrance and all the way along the streamline, but once you get to here, okay, this area here by the fan, the flow is no longer steady, and so applying the Bernoulli equation is no longer valid. So what happens to the Bernoulli equation? Not valid. So today's lecture is really all about how we now deal with that situation. The Bernoulli equation is so useful. We'd love to be able to apply it to a situation where we have moving flow. Yes? Okay, so the question is, does a disturbance travel back along the streamline? What do people think? It's a good question. What do people think? The answer is really no, but it also depends upon the Mach number of the flow. Okay, so in very, very low flows, okay, where your Mach number is very low, okay, yes, you might get some disturbance propagating upstream, but we have to be at a very low flow. Wind tunnels, by design, are looking at rather higher speed flows, okay, and so when you start to get towards much higher Mach numbers, then the disturbance does not have the opportunity to propagate upstream. But I like your question because you're really thinking about the problem. Okay, so in this lecture, we're going to look at how we can use the ideas of energy to analyze systems with mechanical and thermodynamic work. We're going to acquire an understanding of the energy equation for steady flow. So you often hear this equation referred to as the steady flow energy equation. And we're going to learn how to analyze the performance of quite complex fluid systems. And we're going to finish off at the end looking at the efficiency and the mechanical efficiency. Okay? So just to remind you, here is Bernoulli's equation. So you've got P over rho plus a half V squared plus dz is equal to constant. The limits of its applicability, which we're now beginning to understand, is that it has to be applicable to steady, incompressible, frictionless flow along a streamline without heat transfer and without what's called shaft work. Okay, so we'll cover what we mean by that as engineers. You'll hear engineers talk about shaft work all the time. All right, so Bernoulli is very useful. Do not get me wrong in this lecture. Bernoulli is very useful, but we really want to go beyond the limitations of Bernoulli. So, for example, how would we deal with the flows in a hydroelectric generator? So I'll show you this video, but you'll see that we've got fluid in, we've got fluid out, we've got rotational work. How do we analyze this? So let me just pop here. Right, room PC. Let's do this one. Okay. Right, so this is just going to turn off the sound. You can watch with the sound later. So this is a company called Andritz. They're basically one of the top 2 or 3 companies in the world that develop the Pelton turbines for hydroelectric power stations. And I had the good fortune to be able to work for them for a short time. So what you can see is that they've zoomed in on this device, and you can see here's the swirl. You've got the fluid going all the way around. They're focusing in on the different elements of the design. These guys, when they're designing these turbines, they're looking for improvements in efficiency of 0.01%. All right, so you can see all of that's producing the electricity, so that's actually going to the generator itself. And there's the electricity going off into the grid. And so this is a very, very complex system. You can see lots of different types of engineering coming together here. You've obviously got the fluid mechanics of the turbine. Then you've got the electrical engineering as this goes into the national grid or whatever. And then you can see you're producing a whole load of stuff at the end. So this is a really integrated project of engineering, which uses everything that you're learning how to do. Okay, so that's a company called Andritz. Right, let me go back to the other machine. HDMI. So the question is, how do we analyze that? That's a really complex system. So you know you can't go and analyze every tiny little bit in minute detail. As engineers, we have to provide an answer to the people that want to know how much energy is this hydroelectric plant going to generate. As we move forward in this era of awareness about climate change and the need to transfer to renewable energies, you're going to see a lot more sort of small-scale portable versions of these where the efficiency has been perfected in order to maximize the energy that comes out of this for local communities. And you're going to see a lot of that in your career. So how do we deal with it? Well, first of all, let's just think about real flow systems in general. So we've got 2 examples here. Okay, in the left-hand side, okay, we've got a turbine, okay, and it generates shaft work out. Okay, so we say that the turbine work here, so the bottom left, okay, the turbine work here is what's called the work out. Okay, notice the dot because we're dealing with flows of energy. And so that's what you might get with that hydroelectric power station that we saw just before. But what happens if you need to move fluid around from one place to another? We'll see an example of this later. So this means that a pump, we need to use a pump, and the pump needs energy going in. And so this is what is called pump shaft work in, which you can just see here, okay? So this thing will rotate, okay? And as it rotates, it then moves the fluid on its journey from left to right. So very important. And generally, these are rotational machines because they're the easiest to manufacture and understand and to use in an engineering context. And if you think throughout history, humankind has been doing it forever with windmills and water mills. We've been using it all the time. So how do we analyze this? How do we go about it? Well, let's go back to some fundamental principles. And we're going to consider the energy balance for a control volume. So here's my control volume on the top right, okay? And we're going to look at the energy flows in and out. So the change in energy contained in that control volume is given by the difference between the energy in and the energy out, right? So delta ECV is equal to the energy in minus the energy out. So there's my energy in and there's my energy out of my control volume in the top right. Now, if we consider how this changes, okay, over a very small time, delta t, okay, and then we take the limit of delta t as it goes to 0, we get our derivative. Okay, so the rate of change with respect to time of the energy contained in the control volume is equal to E in dot minus E out dot. Okay, so these are the flows of energy in minus the flows of energy out. We're going to be looking at steady flow. Okay, and in the steady flow, everything stays constant with time. That's the definition of a steady process. And so this derivative, dECV by dt, okay, this derivative is equal to 0. So all of a sudden, our energy flow in is equal to our energy flow out. All right, so far, so good. So this is the rate of energy transfer in by heat, work, and mass. Okay. And this is the rate of energy transfer out by heat, work, and mass. So that's what those two terms encompass completely. All right, so let's go a bit deeper. Let's consider a control volume, okay? We've got one inlet and we've got one outlet. So here's the inlet at 0.1, and then our outlet is here at 0.2. And we're going to consider 3 different rates of energy transfer. First of all, we're going to consider the energy of the flow, okay? So this is the mass flow rate times theta, which is basically the temperature. Okay, then we've got the heat conduction in and out, because you might have heat flow across the boundary. So this is Q in and Q out. So here's the heat flow in, and here's the heat flow out. And then we might also have work to or from machines, okay, as we were saying, like a turbine or a generator. So we have shaft work in, and then we have here's shaft work in and here's shaft work out. You can see you put this little sort of circular arrow around the arrow to indicate that that's rotational work going in or out of the system. Sorry, I said it wrong. Quantity theta down here is the energy of flowing fluid per unit mass. Okay. So at steady state, the energy flow rate in must be equal to the energy flow rate out. That's what we derived on the previous page. So we can now just think about our control volume up there and sum everything that goes in on the left and everything that comes out on the right. So this gives us that the heat conduction flow in plus the work in plus the energy the flow in must equal the heat conduction out, the work out, and the energy of the flow out. So what about this quantity theta? Okay, I said this is the energy of flowing fluid per unit mass. Should be the word mass there for some reason. Here, this should be the word mass. So theta is given as the sum of the mechanical energy, which we met with Bernoulli in the last two lectures, plus the internal energy. So a fluid, whether it's a gas or a liquid, has an internal energy. And the internal energy, as I've written here, is the sum of all the microscopic forms of energy related to the molecular structure of a system and its degree of activity. So you know this already. So at a particular temperature, you might have molecules moving around the place. Okay, they have a natural internal energy. So that's what this internal energy is representing here, this U. So our quantity theta, okay, this is the energy of the flowing fluid per unit mass is equal to the internal energy plus the mechanical energy. Okay, all right, so now we can start to go back to our previous page and try and see where we can go with this. So for incompressible flows, the internal energy depends on temperature only. When you get to compressible flows, it gets a bit more complicated, but you'll do that in years 2 and 3. But for now, you can just consider that the internal energy that the fluid has is just a function of temperature. So for systems without any heat transfer to the surroundings, so that means it's adiabatic, so there's no heat transfer to the surroundings. Okay. The mechanical energy losses are converted into an internal energy, making the fluid temperature increase. Okay, you know this because if you get a tub of water and you put a little propeller inside and you rotate it and you rotate it and you rotate it, gradually you'll increase the temperature of the water. So the mechanical energy losses are converted into internal energy, okay, which leads to an increase in the fluid temperature. So that's how these are all related. So the internal energy is a function of temperature. So that means between states 1 and 2, so if we go from point 1 here where I'm standing and then I go to point 2 here, okay, there's a little bit of mechanical loss. That's what we call mechanical loss in joules per kilogram, and that's the difference in the internal energy between those 2 points on our system. So we have a mechanical loss. And then if we multiply this by the mass flow rate, m dot, so here's our mass flow rate, m dot, and we multiply that mechanical loss, okay, then we end up with our energy loss rate for our system. So the mechanical loss rate is equal to m dot into U2 minus U1. All right, so this is our mechanical energy loss rate. Let's keep going. We're making progress. So we said that for a system without heat transfer to its surroundings, okay, that means it's adiabatic, the Q in dot must be equal to 0 and the Q out dot must be equal to 0 because that's our rate of conduction, okay? But it's adiabatic, so we can say that's equal to 0. So those two terms in that equation, we can remove them. They cancel out. So now if we substitute in our expression for theta that we derive, which we said was the internal energy plus the mechanical energy. So here you can see on the left-hand side, we've got W in dot plus M dot into the internal energy U plus the mechanical energy, and we've got the same on the left-hand side. Now we're beginning to get a system that we can work with. We're going to rearrange our internal energy so that it's on the right-hand side. Okay, so all I've done is I've just moved my internal energy terms, those are the ones with U1 and U2, over to the right-hand side. So U1 and U2, so U1's come over to the right-hand side, and I've now indicated it just here. So if you remember from the previous page, this was our mechanical loss rate of energy. So we know that, so we can now substitute that into our equation. Okay, so I'm now going to substitute in for my mechanical loss rate. So that's this term here. And when I do that, here's the equation that we had on the previous page at the top. I now substitute the term in. And here I have my mechanical loss rate just here. All right, so we are nearly done. These terms should be familiar to you inside the brackets, okay, from the Bernoulli equation. So very often in engineering, we're considering the work in to be what we call the useful pump work. In this case, I'm calling it W dot pump, comma, U. Okay, you'll find that very often in textbooks. And the work out is very often the energy to a turbine, okay? So if I substitute all of those terms in, okay, I have on my left that I have the pump work, W dot pump, comma, U, plus the mass flow rate into the mechanical energy is equal to the turbine work out plus the mass flow rate into the mechanical energy on state 2 plus my mechanical energy loss. So this is the steady flow energy equation, right? And it is super useful. You can now go and analyze all sorts of systems that have got machines on it. They've got flows of energy, flows of fluid. You now have the equation to analyze it. You just need to know the values of each of the terms. Okay, now this doesn't look so nice in terms of usability from an engineer's perspective. If you're an engineer out visiting a power station, and you think, crikey, what on earth is my mechanical loss rate? I've got no idea. How am I going to work that out? I don't have the information to hand. So we tend not to deal with all of that, okay? And those are our pump work and our turbine work. How do we deal with these terms as engineers? Okay. Well, if we take our energy equation and we divide through by the mass flow rate and we divide through by gravity, we get this equation. It's the same equation. I've just divided through by m dot and g dot. You can see now I've got these terms. These should be familiar to you. Okay, so this is the Bernoulli equation expressed in terms of meters or head. The same here. And so dimensionally, all of the terms here must have the dimension of meters. Well, that's quite useful. Okay, because the energy equation can be expressed in terms of heads now, okay? So, this is the steady flow energy equation, but expressed in terms of heads. And now you can see, instead of quoting the useful pump work, as we have here, or the turbine work and its rate of there, instead we talk about the turbine head. Here we talk about the pump head. And then here on the left, this is the mechanical loss, and we talk about the head loss. Okay, so all of a sudden, these things are, engineers can relate to that because you can say, the head loss of our system is 50 meters. And it's something that every engineer understands. So the useful pump head is equal to the pump work over m dot g dot. The turbine head is equal to the turbine work over m dot g dot, and the mechanical energy loss over m dot g dot is equal to the head loss. So these are very useful terms that you will need to come to terms with throughout your career. Okay. So we've got two different ways of expressing the same equation. Okay, we derive the first one, and then we just find the energy equation expressed in terms of heads by dividing through by m dot and g dot. So as I say at the bottom, this is valid for systems that do not involve any forms of interactions of energy other than basically forms of mechanical energy and dissipation into thermal energy. As soon as you start to get into sort of the nuclear processes of nuclear energy, this equation is no longer valid. You need a different type of analysis. In later years, we offer you courses on this because it's a specialization of Manchester. Okay, so we've got two different versions of the steady flow energy equation, and you will use each one depending upon the problem you're trying to solve. Engineers use this one basically because it's the easiest one to quote values. So let's just compare now the Bernoulli equation and the energy equation. We actually derive them from very different principles. If you remember, we derived the Bernoulli equation by considering what happens to the acceleration of a fluid element on a streamline. But here we've looked at a control volume system approach to derive the steady flow energy equation. So there's my Bernoulli equation, no friction losses, no work devices. It's only applicable along the streamline. But here, in this particular case, I can apply my steady flow energy equation to cases where I've got work in and work out, and I've got a change of internal energy, so which is basically the mechanical energy loss. That's very useful. So friction losses are included now, and the shaft work are included. But we've derived it using an entire control volume. Okay, so it's piazza pole time. So my question to you this morning is this. We are applying the Bernoulli equation to flow through a ducted fan. Okay, so here is our ducted fan. So we've got our fan, okay, and the flow is coming in just here. We've got points 1, 2 at the exit, 1's at the entrance, and then we've got 3 just in front of the fan, okay? And the question says, which of the following are correct? So we've got A. We're applying the Bernoulli equation for option A from point 1 to point 2. Right. Option B says I'm applying the Bernoulli equation from point 1 to point 3 in the flow. So the question says, which of the following are correct? Is it A only, going from 1 to 2? Is it B only, going from 1 to 3? Is it A and B? Can I apply Bernoulli to both cases? Or can I just not apply Bernoulli at all? So this is the piazza pole, which you should be able to view now. Is it A? Is it B? Is it A and B? Is it neither? Are you still waking up? Right, let's reveal to you how you guys are voting, okay? All right, most of you are saying B only. Okay, most of you are saying B only. However, there's a few who are saying, well, actually, we could apply it to A and B, and there are some saying neither. I'm not applying Bernoulli at all. Okay, so that's very good. I'm quite happy with that result. Because the answer is B only. It's B only for a very similar reason that we discussed at the beginning of the lecture for the end of lecture question from last time, okay? So the Bernoulli equation can only be applied between 2 points where there is no shaft work involved. But here it's very clear you have a fan, okay? So if we wanted to apply it from point 1 to point 2, we actually need the steady flow energy equation rather than the Bernoulli equation. So that's one for you guys to think about, but but the majority of you understood that, so that's good. Okay, so how do we get from the energy equation back to the Bernoulli equation? What's the link between the two? Well, first of all, the friction losses are negligible in the Bernoulli equation, and there are no work devices. So that means that the mechanical energy loss is equal to 0, and the pump work and the turbine work are equal to 0. So when we do that, okay, that's small, so we neglect it. And these two are 0 because there are no devices connected. And so we end up with the Bernoulli equation. So it's reduced to the Bernoulli equation. So this slide, perhaps more than any other, will guide you as to which equation to use. Okay, so when the mechanical losses are small and you've got no pump work, you can use the no shaft work, sorry, you can use the Bernoulli equation. If you understand how we derive each equation, applying it is straightforward. Okay, so let's look at some basic concepts for the fluid systems. On the left, we have a pump. Okay, in the middle, we have an engine, and on the right, we have a turbine generator. So the pump is a bit like what we looked at before. So we put energy into the system to move the fluid. That's what a pump does. And we've been using pumps for thousands of years. And these days, we use a motor to run the pump. With an engine, it's very similar to the pump, except that now we've basically got this fan type thing here, and it's imparting momentum to the flow as it goes through our control volume here. And that's creating the thrust that you will use in any of your analysis. And on the right-hand side, we've got the case of where you've got, let's just say you've got a reservoir. Okay, it can be anything, but here let's just call it water, which flows through the turbine, and the turbine rotates, just as we saw earlier in the video, and that then goes into the generator, creating electricity for us. So those are three very, very basic concepts. The idea is, of course, is to extract or increase the mechanical energy of the fluids. As I mentioned earlier, there's no conversion of nuclear, chemical, or thermal energy to mechanical energy in that sense. Okay, and they can be analyzed by considering the mechanical form of energy only. So quite useful. So let's now look at efficiency. So the definition of efficiency generally is what you get out over what you get in, over what you put in. Okay, so the mechanical definition of efficiency is the mechanical energy output over the mechanical energy input. It's incredibly difficult to get anywhere near 100% here because of all the losses that are involved in the system in terms of the energy output. So if somebody comes to you and says, oh, I've got a 100% or 110% efficient machine, you can tell them where to go. So the mechanical energy output is equal to the mechanical energy in minus the losses. Okay, so the mechanical energy output is equal to the energy in minus the losses. So that means it's the mechanical energy out is equal to the mechanical energy in minus the mechanical losses. So the efficiency therefore becomes our mechanical energy out over our mechanical energy in, which is equal to just this term substituted into there. You can see that this term and this term will cancel. So we're left with 1 minus the mechanical loss over the mechanical energy in. So this is our definition of efficiency. Nice, simple stuff. So in the absence of any losses, there would be 100% efficiency. And as I said, you will never get there. Never, never get there. So let's consider two systems now that are connected together. We have our pump motor system, and we're going to consider how efficiency is used in the pump motor system. So you can see on the image in the top right, okay, we've got electrical power in, which is going into our motor. Then we get shaft work out of the motor, which ends up being the pump work in, and that moves the fluid. Okay, and this motor will have an efficiency, and so will the pump. So we have electrical power in. Okay, so that's W-elec in. Okay, and then we get mechanical power out. There's an efficiency of that process. It's not a 100% efficient process for anything. Okay, and the efficiency of that process is equal to the power out of the motor over the energy in, which is the electrical energy in. Then we've got the pump. Okay, so this gives the fluid an increase of the mechanical energy, but of course there's an efficiency attached to that as well. So the efficiency of that part of the process is equal to the mechanical energy, change in mechanical energy out over the pump work in. Now you notice up here I've said, well, that the motor work out must be equal to the pump work in. And in general, that is true. You can assume that fairly safely. So the overall efficiency of the system, that's got to be the mechanical energy, the change in mechanical energy of the system over the initial energy in. So that's the electrical energy. So that's what I have here for my combined pump motor system. Now, if I substitute in my expressions, okay, well, what I'm actually going to do is I'm actually going to multiply top and bottom of that expression by 1. Okay, so I've just multiplied it by the motor work out, and I've divided by the motor work out. So I've multiplied the whole thing by 1, because now I can see how I can substitute in my expressions for the efficiencies above. So the motor power out is equal to the pump work in. And if we substitute in our expressions, I've got my motor work out here, which goes here. I've got my pump work in here, which is I now put on the right-hand side. Okay, so I've just switched these two terms around on the bottom. And this now is equal to my motor efficiency, and this is equal to my pump efficiency. So my overall efficiency from my system is equal to the multiplication of the efficiencies of the two devices. So this is a very useful bit of analysis. And then we're going to look at a turbine generator in very much the same way. Okay, but this is where mechanical energy of the fluid gets turned into electricity. So the turbine work out, okay, so the work out of my turbine here goes directly into my generator just here, which then goes into the electrical power grid. So the mechanical energy extracted from the fluid, okay, that's delta E mech fluid, gives me some mechanical energy out from the turbine. And there's an efficiency attached to that process, as we had before. So that's the turbine work out over the mechanical energy extracted from the fluid. Then when we go to the generator, we get electrical energy out, and there's an efficiency to that process as well. So the generator has an efficiency. So the generator efficiency is the electrical work out over the shaft work in. And shaft work in is equal to the turbine work out because these two are connected. So my overall efficiency for my system is the electrical energy out over the change of the mechanical energy of the fluid. So I can now substitute in, very similar to what I did before, by basically multiplying by 1 and having multiplying top and bottom by the same quantity, because these two are equal. I can now substitute in for my efficiencies. I've got my turbine efficiency and my generator efficiency. So the efficiency of the combined system is less than the individual efficiencies by definition, because they're all less than 1. So this is the way that we go about analyzing composite systems. We've got multiple devices now in our system, and we can analyze it. Now, just a little word, because it sometimes confuses people, on converting the heads of fluid to the energy flow rates. The mass flow rate, m dot, okay, of our system must be equal to the density of the fluid times the volumetric flow rate, which in many analyses in this particular sort of application of steady flow energy equation is given V dot flow, okay? So it's the volumetric flow rate, and that's measured in meters cubed per second. So we can substitute in our expression for m dot into our expressions for the heads that we had earlier, okay? So there we have our expressions there. So if we rearrange and we substitute in for our expression for m dot, okay, so we're rearranging our expressions there. So for example, the useful pump work is equal to m dot g times the pump head. We then substitute in for our expression for the mass flow rate, m dot, and that gives us our energy flow rates, okay? So if you have a problem that we'll see in a second or two, where the engineers are quoting the volumetric flow rates, which is quite often what they do. They say, my fluid is water, my volumetric flow rate is so many meters cubed per second. You then know how to calculate your energy flow rates. Okay, so there is our mass flow rate substituted in. So a really great example of this, and you see this replicated all over the world, is a hydroelectric power station. This is Electric Mountain in North Wales. And this is an amazing place to go and visit if you get the opportunity. They have a visitors center there, and you see engineering on a vast scale in operation. But it's in a very mountainous region, so you've got a lot of rainfall off into the reservoir. And so here you can see the reservoir, and this is actually the building that houses the generators. And here you can see, here are the massive generators. And so the fluid is going through these generators, these turbines, and then creating the electricity. So how does this work? And it's been existing for many years now. Well, during the day, okay, here you have the level of the reservoir, and the water from the reservoir flows down due to gravity through the turbine, generating electricity for free. And how much better does it get? You get free electricity, and that goes into the turbine. So they're generating electricity when we, the people, need it most. Okay, so the consumption of electricity is greatest during the daytime. But then at nighttime, we're all sleeping, hopefully, mainly. Okay, so at nighttime, they then use the surplus, the extra electricity that is generated, to pump that back up. So the turbine becomes a pump, and then it goes back up. Okay, so it's a very clever system. So we generate electricity during the day when people need it for free. We use the excess, the extra energy, then to pump the water back up again to the reservoir, and we do the same thing every day. And it's a very, very efficient system and a way of generating electricity. But we need to be able to analyze that as engineers. Yes? Can we not? What, sorry? My guess is that they've worked that out, and it's not an efficient system. You probably could do it. However, you'd need some rather amazing energy storage devices, electrical energy storage devices, to do that. Based on this, bringing all of this together. So in a hydroelectric power plant, 100 meters cubed of water flows from an elevation of 120 meters to a turbine, where power is generated. The total head loss of the system from point 1 to point 2, excluding the turbine unit, okay, is determined to be 35 meters. So this is how engineers talk. If the overall efficiency of the turbine generator is 80%, estimate the electrical power output. With all of the equations that we've derived today, this system should be fairly easy to analyze. So we're going from point 1, okay, the fluid is going down here at 100 meters cubed per second. Here's our turbine going into the generator, and we want to know what's going on there. Okay, so we know we've got shaft work, okay? We cannot apply Bernoulli equation. We have to apply the steady flow energy equation because we have a turbine. So let's start by making our assumptions absolutely clear. You have to do this as an engineer, state what your assumptions are. The flow is steady, it's adiabatic, and it's incompressible. The water level is constant in the lake for the time period that we are considering. The lake is pretty big, so that's okay. And then step 2, we will then apply the energy equation between points 1 and 2. So convenience, we're going to take our z is equal to 0. That's our datum. We're going to take that at point 2. Okay. So at point 2, that's where z is equal to 0, which is going to allow our system here to be much easier because z2 will be 0. Okay, so there's our energy equation, and we're going to consider those terms one by one. Okay. So first of all, let's identify our known quantities. First of all, we know what the pressure is at points 1 and 2. It's atmospheric pressure. Bingo, done. We've identified that one. In comparison to the velocity of the falling water, which is accelerating under gravity, we can safely assume that the velocity of the water at points 1 and 2 is 0. Okay, this is basically still, okay? So V1 is equal to V2. They are approximately 0. Okay, so far so good. There's no pump work into the system. So the head due to the pump is equal to 0. We're just taking energy out. So this is turbine energy out. And we can now start substituting our terms in and cancelling. Okay, so Z2 is equal to 0. We set up our problem, so that was nice and convenient. P1 is equal to P2, so that those terms cancel because we've got the same pressure either side. Okay, V1 and V2 are both equal to 0 because we can safely assume that those velocities are 0. The pump, the useful pump head is 0. And so we are left with a very simple equation. Z1, which is the height of the water above our datum, must be equal to the turbine head plus the mechanical losses. That's the mechanical head loss. So now we calculate the shaft work out from our turbine using what we know. So the turbine head is equal to Z1 minus the head loss. We just worked out this equation and we've rearranged it now to find the turbine head. So this is 120 minus 35. We just put in our values and we get the turbine head of 85 meters. So therefore, the shaft work out of our system must be equal to the mass flow rate G times the turbine head. Well, in the 2 or 3 pages ago, we worked out that our mass flow rate must be equal to the density times the volumetric flow rate. So now we just substitute in all of our terms. So the density is 1,000, the volumetric flow rate is 100 meters cubed. Okay, so there's our 100 meters cubed. Gravity is 9.81 and the turbine head is 85. So we end up with 83,000 kilowatts. And the last part of the question was said, okay, we have the overall efficiency of the system to be 80%. Find the electrical power output. So we know that the electrical power output must be equal to the efficiency for our system times the work that's going into the generator. That's the turbine work, which we've just worked out. And so we end up with 66,000 kilowatts. So in each step of this worked example, we've just used what we've been developing in the lecture. Okay. So in this lecture, we've considered different forms of energy. We derived the steady flow energy equation. We looked how it compares to Bernoulli, and we considered the mechanical efficiency. But I have my normal end of lecture question for you. Let's think about these two cases. Okay, this was the turbine we looked at here, and then this is a real aircraft. We assumed that the fluid was ideal, was pure. Do you really think that the water coming into this turbine is pure water? Do you really think that the air going into the turbine of the jet is pure air? All right, there's a very famous case a few years ago where that was definitely not the case. So the question is, what happens if the fluid is not pure? Okay, so what happens if it's not pure? So I'd like to thank everybody in the audience who's wearing a mask. We do appreciate it. See you next week.